Hey, welcome Math or Physics 20, sorry. So right now we're going to go over this course review package here. Some of you might have seen the answers already, but I'm going to go over how to get those answers. And if you don't want to follow this video, I'm sure there'll be a PDF version of this document there as well. All right, so let's see what we got here. So the first little thing just talks about certain things like make sure you're converting units, right? Make sure you have proper scientific notation. Make sure that decimal is immediately after that first sig dig. Zeros don't count as sig digs unless they're trailing, right? So the first digit can never be a zero. So in this case, you can see it's 1.23, and the point is right after that first one. Here are the rules for sig digs, right? Most of the time we're doing the multiplication one, and then we got some formula manipulation. So that's what we're talking about here. So in these kind of questions here, pretty straightforward questions. Like in question 1 here, they just want us to rearrange this equation where it says x is equal to g over t. So you're trying to get t by itself, right? So we have to manipulate this formula. So to do that, I'm going to multiply both sides by t. Okay, so the t on this side cancels out, and we get a g left on that side. You can see why we're doing this later. We're not solving for g, we're solving for t. On this side, x times t is just going to be x times t. Okay. So now what we got it up to the numerator. Then we're going to take that and we're going to divide the other piece. So what we're trying to solve for has to be in the numerator. So we solved it up and we divide by x on both sides. This x here cancels out now. So now we're left with the t, and then we got g over x. I'm sure this shortcuts. Lots of teachers say we'll just do a swap. All right, times up, divide down, do a quick little shortcut, done. But these are all the steps that you're actually doing. Right, you multiply it up and then dividing everything else down. So on the other one here, we got x is equal to a, b, c over d. Okay, and we're trying to solve for b. Now you see here the b is in the good spot already. Like up here, the t wasn't. It was in the denominator. But now it's in the numerator, so that's fine. So it doesn't matter which side you get the variable by itself, as long as it's by itself and in the numerator. So my first step on this one is get rid of the offending divide by d here. So that cancels out. But if I do it to one side, I have to do it to the other side. All right? So what we've done is kind of created what we call a linear equation, or not really linear, but a flat equation, right? It's all one line. Then, rather than dividing both by a and then dividing by c, you might as well just divide by both at the same time. So that crosses off the a, that crosses off the c. So you just have to do the same thing to the other side. So my question now, or my answer here is b is equal to dx over ac. All right, there we go. That's question 1. Question 2, putting this into scientific notation. So when you put in the scientific notation, you're just pretty much just counting decimals. You can see here, I'm going to move this decimal place back. 1, 2, 3, 4 spots. Because I went backwards, makes the number smaller. So 1.7 times 10 to the negative 4, because I skipped 4 times, right? 1, 2, 3, 4 times backwards, negative 4. Whatever the units happen to be. I'm just going to write down the units here, but we don't know what they actually are. So you can see that decimal has to be immediately after that first sig dig. Here we're just solving, we're just adding these numbers together. So this is like 40,000 plus 3,000, so that's 43,000. But because of the sig dig rule, since we're adding, this is just 4,000 again, or 40,000, because you're going to be rounding it. But I'm not too concerned about what these answers end up being. Okay. Let's see what that's what they do. So a here, since we're adding, it'll end up being 4.3 times 10 to the 4, because it's 43,000. But because of the sig dig rule, it just goes back to being 4. Just because you just have no decimal places. Just the rule. All right. Same thing with minusing. If there's no decimal places in one of the numbers, so one of your answers will have no decimals as well, or they should have no decimals. I'm just looking at the answer key. I wonder why they included the decimals, but they did. So this says the least number, there's no decimal places there. So minusing that out, it'll just end up being 6. Okay, so 6 times 10 to the 9. Cool. Multiplying and dividing. So again, least number of sig dig. So this one has 1 sig dig. So when I divide these two numbers, you're going to get whatever 3, well, it's typing in the calculator, a huge number, 300 million, that's just the speed of light essentially, divided by 1.2 times 10 to the negative 7. So I get 2.5, but I need 1 sig dig. So I'm going to write down what it is when you actually do it with the decimal included, times 10 to the 15. But because of the 1 sig dig, this is going to be 1 sig dig for my answer too. 15, sweet. Okay, I should probably show that middle step for this one too, where that happened there. So this would be 6.3 times 10 to the 9, but because of the 1 sig dig, 6 times 10 to the 9. And the last one, there's 2 sig digs in this one, because you're multiplying, you go with the least number, so 4.7 times 10 to the 12 times 8.678. Make sure I type all the numbers properly, times 10 to the 6. So you get a bunch of decimals here. So you get like 4.7 or 0.7866 times 10 to the 19. But because of the number of sig digs, there's supposed to be 2. You get 4.1, this decimal right here, right there, 4.1 times 10 to the 19. Yeah. Unit analysis, let's see. Okay, so we're changing between them. So this still throws people off. Like, remember when we're doing most of our math, kilograms, but everything else doesn't have any prefixes, right? Not kilometers, not kilojoules. It's just regular joules, regular meters. The only thing that needs kilo, it's all the math because of the newtons and stuff, is our grams. So looking back on my formula sheet over here, I know what a kilo is. It's times 10 to the 3, right? So there is a rule, which I don't teach my physics students too often, is that if I'm going one way, so say 1 meter is equal to 1 kilometer. It says on there, it says it there, it says 1 kilometer is 1,000 10 to the 3 meters. So you don't necessarily need this. You can just see on the formula sheet they don't bother putting the meters part in there. But if you're going this way, you're timesing. If you're going backwards, you're dividing. As long as there's a 1 on the left-hand side, this works. Right? So if I want to go from grams to kilograms, I'm going to divide. All right? So it's going to be much smaller. So divide by 10 to the 3 or divide by 1,000. So this will be 1.2 times 10 to the negative 4 kilograms. I'm dividing by 1,000. So if you look at the sheet up there, it says that 1 centi. Is that centi? Yeah, centi. They don't have the number there, but it's 1 centi. And you can put meters there if you want to. Might as well, meters. All right. Oh yeah, this was in grams over here, and this meter doesn't matter. Is times 10 to the negative 2, right? That's what it says, negative 2 meters. Same rule. If I'm going forwards, I times. If I go backwards, I divide. So I'm going to times by this times 10 to the negative 2. Times the 10 to the negative 2. This is fun, my calculator. There you go. So I get 0.0135 meters. Essentially it's just divided by 100, but the same rule. So that's how those things work up there. Proper sig digs. As long as the units are good, you can add them together. Looks like we can definitely add these together, and they both have 2 decimal places. So the answer will have 2 decimal places. But then you got to watch out for units, right? So if you add in the 2 kilograms together, you're going to get kilograms. If I multiply these two, and there's only 1 sig dig here, so my answer is going to only have 1 significant digit here. 2.08 times 0.04. I'm going to get, this is the answer when I multiply it, 1.1208 Newton meters. Right? And then proper sig digs 0.1 Newton meter. That's it. 4 people each ate this. How much is the total mass? I guess I'm multiplying this, right? So 4 times 432. So when I did this, I get 4 times 432. I'm going to get 1,728 grams, which, if you want to put in kilograms, follow the rule up there. I'm going backwards. I'm going to divide by 1,000. Right. 17 kilograms, but with proper significant digits, 2. 2 kilograms. And that's it. The answer key always says 2 to times 10 to the 3. That doesn't make any sense. That's okay. Let me just fix that up there. Okay. Find angle B and angle A. Okay. So there's 2 ways to find angle. One of the angles after you find the other. Right? You can use the 180 rule or not, but to find an angle, first of all, let's say we're going to find angle B. So here's, let's stand in that corner over there. So I'm right here. So once you've determined what angle you're going to find, you can label the triangle. So I'm trying to find angle B. Across from angle B, that's going to be my opposite. And then anything that's across from the 90, or what looks like the 90, is going to be my hypotenuse. And then over here we've got the adjacent. I mean this. So I have all 3 sides. So I can use whatever ratio I want here. I can use, and this is a 3, 4, 5 triangle, so this is true. So I can use whatever ratio I want. I don't know where it is up behind me there. I'm just going to pick sine. Why not? Sine B. Okay, since we're trying to find B, I'll just put a B there rather than theta. All right, so B is equal to, and I'll just fill out everything we have. So we have 4 on the opposite side, we have 5 on the hypotenuse side. To get the B by itself, remember, to do that, we have to move that sign over to the other side. We've got to get the B by itself, like rearranging an equation. So we've got to do the inverse of sine. The inverse of sine cancels the sign out. So I get B by itself. But whatever you do to one side, just like we did when we rearranged these equations, you have to do to the other side. So I've got to take the sine inverse of both sides. Okay, so angle B here is going to be the sine inverse of 4 over 5. Oh, I got somebody coming in my door. This one's there. All right, so that angle is going to be 53 degrees. It's 53.1, etc. They don't have many. Sig digs and angles is different than sig digs and the numbers, but they don't have decimals, so let's not use decimals. Find the other angle, use the 180 rule. So angle A is going to be 180 minus the 90, that's already there, minus the 53 we just found. So angle A is going to be 37 degrees. There we go. All right, so this next part here is all about kinematics. So our first chapter, and then it gets into more kinematics, and then we got some 2-dimensional questions here. When it gets to vectors and our t-charts, there's a lot of kinematics, right? All right, so let's see what we have here for answers. Yeah, so our first one talks about uniform motion, right? Uniform constant speed or velocity. When it comes to that, when you don't have acceleration, when you have 0 acceleration, where acceleration is equal to 0, usually that's the better way to write this. Okay. Our velocity is going to be equal to our change in our position, or change in our distance, divided by our time, right? So if you look at that very carefully, the formula, the change in the distance on a displacement time graph here, the change, like y minus y, of our height is our change in our displacement. And then on the bottom, we have change in time. So therefore, our slope of a displacement time graph, which is change in displacement over change in time, must be our velocity. It's going to be very important later on. And if I move in at a constant velocity here, then my velocity is not changing. So if I look at this very carefully, that my change in my velocity of this one is 0, and therefore my a is equal to 0 as well. So my A would be 0 in this case because I don't have a change of velocity. We'll talk about that formula for change of velocity later, right, which you should already know. Or sorry, for acceleration, which you should already know. Then is in sketch, find the slope at an instantaneous velocity. You don't really need to worry about that. It's like a curved graph, and I think it's a curved graph. Maybe it's not. No, I don't think it actually is. Find the slope of that line. What type of motion is displayed by this graph? Okay, we don't have to worry about that. If you want to do that, you can. Probably find a line of best fit. All right, so a car here travels from Edmonton to Calgary. It takes 3 hours and 20 minutes to make the trip. What's the average speed? Okay, that's an easy one to do, right? It doesn't specify the units it wants to be, so maybe you can put those, keep them in kilometers per hour, or you can make meters per second. It's totally up to you. But to find that average speed, you take your total displacement or total time traveled. If you're going from Edmonton to Calgary, you're going south, I guess. Well, you can go 300 kilometers here. So it's speed anyway, so I don't have to worry about direction, right? And we're going to divide it by the time. Now the problem with this is we have 3 hours and 20 minutes. I want to combine them together as one thing. You can make it all minutes or all hours. So if I want to add these together, I'm going to just divide that by 60. And divide by 60. Get in total 3 hours and 3.33 hours. Okay. Then take the 300 divided by this, and we're going to get, on average, 90 kilometers per hour. Okay, sig digs are a bit weird because of the 3 hour part and 20, so I'm just going to stick with 2 sig digs here. It rounds pretty nicely. So 90 kilometers per hour. Okay, the next one here, I like this one because it's asking for the speed and the velocity, but we have 2 sections of travel here. One part's going north, one part's going south. So if I want to find that average speed or average velocity, I need to find the total displacement and the total distance. So what I'm going to have to do here is I'm going to break into the 2 parts. We got part 1 here, and then we got part 2. I've got to figure out how far they traveled in each section. All right, so the first one, since I'm using v is equal to d over t, and then d is equal to v times t, I can find out how far we traveled by taking 68 kilometers per hour times by 1.5 hours. So we got 120 kilometers, and this one is north. All right, so that's going up, right? And then the second section, same idea, v is equal to d times t. This one's going south though, so 6 times 2, 112 meters, or kilometers, sorry, south. So the 2 questions we have here is what's the average speed and what's the average velocity? When dealing with velocity, direction matters because now we have to worry about they're going opposite directions. So I go up and then I come back down. Just like displacement is from beginning to end. It doesn't matter how you get there. Right? I'm just going up and down. So if I want to find the velocity, I'm just going to do that right now over here, I have to take into account that they're going opposite directions. So I could say that north is positive. If I said that, then I would have 120 kilometers, that's positive, plus a negative number. So I'm plussing a negative. You're always adding numbers, but there might be some negatives in there because that's what's south. And then the total time, when it comes to total time, they're always scalar. Direction doesn't matter. So I'm just going to add those 2 numbers together and get 3.5 hours. So my velocity here, it's my displacement. Let me just find that out. It's only 10 kilometers in the south direction divided by the 3.5 hours. So my average velocity is 2.9 kilometers per hour because it was negative south, right? So very important because it's the velocity. Now for the speed, I'm just going to add the numbers together. 102 kilometers plus 112 kilometers divided by my total time. So my total distance traveled here is 240 214 kilometers, 3.5 hours. So 214 divided by 3.5, about 61, which makes sense. Somewhere between the two numbers, 61 kilometers per hour. Okay? So be careful about when you use a sign convention and when you don't use a sign convention. Speed, distance traveled, velocity is displacement. Okay, let's keep it going. Okay, so now if I start accelerating, then I'm going to have different shaped graphs, right? So in accelerated motion, a displacement time graph here, you'll see a curve because every second interval, so imagine like every 1 second, if I just split this into even sections here, then you can see that in this 1 second interval here, whatever this is, I'm moving a certain distance, right? So this is my distance I traveled. And in the next 1 second interval, you can see that the distance I traveled was further. It's changing, right? Or let's see this 1 second interval right here, that distance there is smaller, right? So my distance I'm traveling, that displacement, is changing over time, right? Like it's changing larger and larger numbers, or getting smaller and smaller depending on which way you're accelerating. It's not the consistent number. So you get this kind of curved graph here. The velocity time graph, right? In a velocity time graph, we have two things we can analyze, right? Our slope, now we kind of talked about this before, our slope, which is my change in my velocity, and this is my change in time, it's my rise or my run. So that means the slope, which is change in velocity, divided by change in time, that's my acceleration, right? So my slope is my acceleration. Now, they talk about this area here, 1/2 base times height, or 1/2 length times width. That there is how far you move. So I didn't do that up here, in this equation up here. Here they put area as base times height. The reason they have that there is if I look at this equation, and I rearrange it, because here my length here is my velocity, and just nice constant velocity, that's velocity. And then my width here is time. If I multiply those together, I get v times t, which, if I look at the rearranged version of that, that's equal to d. That's equal to my displacement, how far I've traveled. So my area of a velocity time graph is my displacement. Right? And that works for triangle shapes too. Right? That one's nice and easy because there's this constant speed, constant time is always constant, so length times width. But in terms of like a shape like this, well, if you find the area, you also find, because the area is still the same thing, it just happens to be 1/2 because you're accelerating from one speed to another. Nice constant acceleration is 1/2 base times height, which is like 1/2 v times delta t again, which is also still equal to displacement. Right? So my area, displacement. So area is still displacement. So that area is displacement. Now, we could do some things with acceleration time graphs, but we never really did. But if my acceleration is constant, then I'll just have a flat line there. If it's not, then we get what we call a jerking motion, and then that can go to a jerk graph, and then snap, crackle, pop graphs from there. But. All right, so what we did in class, we looked at these graphs and we developed these 5 formulas here. You only see 4 here, but one of them is not written down. We don't use that often, but it is the VF formula, VFT minus 1/2 AT squared, but it's the same idea. If I'm given a final velocity rather than initial velocity, I use that one. So we got these 5 equations. We have 5 unknown things in most questions, right? We have acceleration, time, displacement, VI, and VF. So we have these 5 variables that we deal with. And all you really need is 3 of them to find a 4th one. You can just always ignore the 5th one that you don't need to find. So when you're doing these questions, that's what we got to figure out. Which of these 5 equations am I going to use? So, well, what do we have here? So it reaches a certain velocity from rest. So we got some keywords, right? We got rest. So if it's at rest we're going to start at 0. We've got a final velocity of 100 kilometers per hour, which I'm going to want to change. Remember, we want to change that. You could divide by 3.6. In this case, it's 27.7 repeating meters per second. Okay. Here we have time. We have 14 seconds. And we're looking for what's the acceleration. So we can see we have three things: VI, VF, and time. Find a formula that involves that. So it looks like this first one, VF minus VI. Remember, that starts as delta. So remember, the delta V over T is VF minus VI over T. And we just plug all the numbers. We don't even have to rearrange it. Right? Now, acceleration is a vector, so it should have directions. Let's just say forwards is a good direction here. So I'm going to take this velocity that we have, minus 0, divided by the 14. So it looks like my acceleration is 1.98. I'm going to write down a bunch of decimals here, because I messed up and I forgot sig digs to start off with. There's lots of decimals there. Meters per second squared. So rounding this up, that rounds the 9, which also rounds up that. So it ends up being 2.0 meters per second. I'm just going to say forwards kind of as a default here, because acceleration is always a vector. Ball rolls. Okay, so rolls down. So 90 centimeter incline. It took 3 seconds to do that. We gotta do an assumption here. Let's make an assumption that the VI is equal to 0. I know it'd be nice if it said a ball starting at rest rolls down and inclining that. What's the acceleration? But that's what you're gonna have to do here. We're just trying to find A now. Okay, so what's a good formula here? It looks like it doesn't have any VF in it. No VF. So a good formula to start off with this one would be D is equal to VI T plus 1/2 AT squared. Okay? And then we're going to rearrange this equation. What's nice about this is that I'm solving for A, not T. But even if I was solving for T, because VI is equal to 0, that cancels out. So this is gone because VI is 0, which makes my equation just a little bit easier to rearrange. Right, we're still trying to solve for A. So right now I got the A in the good spot. It's in the numerator, but I got all this stuff around it. So I got to move that stuff to the other side of the equation. So I'm going to divide by the half. So I get D divided by the half. Right? And at the same time, I'm going to divide by the T squared. You get the A by itself. So now I'm going to divide by the half and the T squared. I'm going to divide them both down to the bottom. Okay? And there's my equation. Technically, you can just times by 2. I guess I could have done that, get rid of the half, but it's totally up to you. Now the 90 centimeters, what does that have to be? Well, it's got to be in meters, right? So this, I'm going to write down here, 0.90 meters. We divide by 100. And divided by the time squared. So 0.2, let me see, it's 20 meters per second squared. And it looks like it's going downhill. This is rolling down the incline. Okay. Car is traveling at 36 kilometers per hour. Okay, that seems like it's its initial velocity. I'm going to divide by 3.6 again, so in this case I get 10 meters per second. It's got an acceleration this time. It accelerates at a certain rate. Let's just see the final speed. Let's assume it's increasing its speed because they're not giving us the direction here. Let's assume that I'm going this way, I'm going to accelerate this way. So right now everything's kind of going the same direction. I've got time, 6 seconds. And we're looking for that final speed, and we're looking for the distance or the displacement covered here. So we're looking for both. But we've got 3 things. So pick one to start off with. Let's say I'm not going to find D. Let's find that doesn't have a D in it. So if I'm going to solve for the VF, I'm going to pick maybe this one to start off with because it doesn't have a D in it. That's the VF minus VI over T. So I'm going to rearrange this. I'm going to times both sides by t. So I'm going to A delta t. Because right now, I have these parentheses around this VF and VI. I can't move them out of there until I get rid of those parentheses. That vinculum's in the way. To get rid of it, let's get rid of the divide by t. So I end up with VF minus VI. And then I'm still trying to solve for VF, so I'm going to add over this VI to the other side, so plus VI. There you go. That looks pretty good. So we plug all the numbers in there, so I got 2.5 times the time plus the 10. So my VF is 25 meters per second. Now what's nice is because they start off in kilometers per hour, you probably should end up in kilometers per hour. So let's just do that really quickly. So my final velocity here is 90 kilometers per hour. Okay, didn't have to do that probably. Next one, I want to find the displacement. So what I'm going to do is I'm not going to trust my VF, right? So don't trust an answer you just got. Pick another formula that involves the stuff that was given to you in the question, right? So let me just put my face out of the way. So 1/2 AT squared. I'm going to solve, I'm solving for D. I don't have to rearrange it. Just put all the numbers in. It should be good. Okay, so I got 10 times the 6 plus a triangle at the top there. That's what that other part is. That's my acceleration. 1/2 times my 2.5 times my 6 squared. Okay, I'm going to show you times squared. So my displacement I covered is 105 meters. Done. There you go. I think we're pretty. Yeah, let's try the next one. Free fall questions. Okay. So when it comes to free fall, as long as we're near the surface of Earth, gravity is 9.81. It doesn't have to be, right? We could be in different planets or a different place somewhere else. So that could be a different number, and we may have to calculate what that number is by using the literal G is equal to gm over r squared formula that Newton kind of discovered. Okay. So look for these keywords when they think about projectile motions and free fall stuff. Is like if the object falls or if it's thrown upwards, right? Then you're going to get like different things happening. Like when it falls, VI is equal to 0. Gravity is downwards, 9.81. It's always down. Gravity is always down. So now you have to decide, do you want this to be negative? Do you want it to be positive? It can be negative or positive, doesn't matter. You could just say down is positive, but then everything up is negative, right? Let's just say that. So let's say down is positive here. Hits ground with a final velocity of 85 kilometers per hour. I'm just going to quickly change that into meters per second. Cool. How long did it fall? So a t. Question. So find a formula that doesn't have d in it. There's no displacement. So that's going to be my final minus my initial over time formula. And we're going to do a little rearranging, get time. So VF minus VI divided by A. So I'm going to times the t up, divide the A down. Okay, final minus initial divided by 9.81. 2.4, that's it, 2.4 seconds to fall to the ground. All right, an object thrown upwards, certain velocity, how long did it continue to rise? So in this case, it was kind of like, how long did it take to get to that max height? Because once it hits the max height, it's going to start coming back down. So how long did it continue to rise? So this is like at the max height. So it's not trying to find the max height, we're just trying to find the time to get there. But what's interesting about the max height, because it has to change direction, my VF is going to be 0. If we just talk about vertical stuff, it might have some horizontal motion, not in this question, but it could be thrown a little bit in the horizontal direction, which means it might be moving horizontally up there. But vertically, it's 0. So the initial velocity, 14.7 meters per second. Time, A. Oh, if it's thrown upwards and acceleration is downwards, something's got to be negative here. So let's just make gravity negative now. Up here, everything was moving down, right? So we made everything positive. But here, something's got to be positive, something's got to be negative, right? Because they're opposite directions. And we're trying to find time. Okay, same formula. It's kind of weird. You think you could pick a different formula here, but that's okay. So So same rearranging, right? I'm using for both these equations. Okay, so final 0 minus my initial. So 0 minus 14.7. So we got a negative number on the top. Okay, so that's what happens here. And then we divide by a negative 9.81. So nice and convenient that we get a positive number. So it's in the air for 1.5. Ooh, 3 sig digs. Watch out there. 3 significant digits. Ooh, 5, 4, 9. So it's actually 5, 0. That's kind of nice. Okay. Bowling ball is, a student drops a bowling ball and a grape. The grape hits the ground 4 seconds later. How far did it fall? How long did it take the grape or the bowling ball to hit the ground, and how fast did it hit it? So they're essentially the same, because remember, it doesn't really matter if we ignore air resistance and stuff. It doesn't matter the size of the objects, right? If I drop them, they both fall at the same rate. So it doesn't really matter if I'm talking about the grape or the bowling ball, right? So let's see, time is 4 seconds. VI, because I'm dropping it, drops, is 0. Acceleration, downwards, I'm just going to say downwards is positive because everything is moving down. There's no other direction here. And we're looking for a few things, right? How far did it fall? We're looking for D. What's its final velocity? Right, so I've got to find each one of those two things. Sorry, excuse me. So how far did it fall? That's a pretty easy one. Let's do that one first. So D is equal to VIT plus 1/2 AT squared. Don't even have to rearrange it. Awesome. So 0 times 4 is 0. Okay, that'll help. Okay, 1/2 times 9.81 times the time squared. So it fell for 70. Oh man. Okay, I'm going to write down the decimal, but there's only 1 sig dig here. That usually never happens, but 78.48, but that's 7 times 10 to the 1 meters. That's ridiculous. That's the way the cookie crumbles here. Okay. Now, how fast was it moving? So VF, what was that? So what formula would I use? Not using D, right? So I'm going to go back to my original A equation here. And trying to solve for VF, right? What's nice about VI, it's 0, but I'm going to rearrange it as if I didn't know that, right? So I'm going to times the VF, or T up first, sorry, and then add over the VI. Okay, and then just adding over 0, honestly, but 9.1 times the 4. So it's going to hit the ground at 39.24 meters per second. This is down, right? It's just not fast, but I'm going to put direction in just to be safe. Oh, proper sig digs. Oh, man. So 3 or 4. I don't know why they didn't put 0, 0 there. 4 times 10 to the 1 meters per second down. What did they do? Did they just ignore that part? Let me just look at the key on the other side of my page here. And they just kind of ignored that. And they just took 3 sig digs and all the answers. Anyways. A stone is dropped from a balloon that was also descending at a certain time, right? So because the balloon was descending, if I'm on this balloon, so I'm on this balloon, and the balloon is moving downwards when I let go of it, when I let go of the coin was initially also moving downwards too, because it was in my hand, and I was moving down. So when I let go of it, the coin was also moving down. So my initial velocity, even though I said dropped, because the balloon is descending, my initial velocity is initially down. Okay, so let's go and go down. Acceleration is also down. So I don't have to put a negative there. I can just say that's positive. Okay, but that's going down. That's going down. The balloon is a certain distance above the ground, which is also going to have to go down. So 700 meters. So everything's just a positive number because everything's going down. That's nice. How long does it take to hit the ground there? So t is equal to a big question mark here. What's a good formula to use? So I'm going to use this formula here. Now, the problem with this formula in this time, or at this time, if I'm going to solve for time, because vi is not 0. If it was 0, just cross that term off, solve for time. Easy. You've got to take the square root eventually. But because vi is not 0, I can't just cross that term off. I have a t in one term, I have a t squared in the other term. How do we get the t's all by themselves? If d was equal to 0, then maybe I can divide a t out. But I can't. There's no way to get rid of those t's. So, what do I do? Well, two ways to do it. Put all the numbers in and graph it. Try to figure out where do they intersect each other. Or find something else, the VF, and then use a different equation with that VF. Two different ways to do it. So if you don't, or I guess the third way, quadratic formula, right? Number 3, quadratic formula. If you want to do that. It's not even on the formula sheet, so you're going to have to try to memorize it if you want to. But I would probably suggest graph this here. So graph. Or find VF first, right? So one of those two things to do first. I'm going to do the find VF first because I don't want to pull up my graphing calculator. And I don't want to deal with the quadratic formula. So I'm going to do the VF first. So I'm going to find a formula to find VF. So that's going to be my VF squared is equal to VI squared plus 2AD. Everything's positive here. I'm going to take the square root of all of that. Eventually, what does that end up being? So it's 20 squared plus 2 times 9.81 times 700. Okay, and I didn't do the square root yet. So it's going to hit the ground with a velocity of 118.8865 meters per second. Now there's a plus and minus here, right? So when you take the square root, there's always plus and minus. So we have to kind of think about which way is it going to go. I said down was positive. It's going to hit the ground downwards. Okay, that's a positive number. You just have to make sure you know which one we're talking about. So this is definitely downwards. Okay, so now I have a VF. I can use, I can use this formula to find time, right? A is equal to VF minus VI over T. I'll rearrange it for T, VF minus VI over A. Okay, so I got my VF, got my VI, okay, do that, divided by my 9.81, and I get 10.1 seconds, 10.08, but we need, 10 seconds, so just 10 seconds. I'm going to write down more decimals here, just so you can confirm you got the same answer as me, but it is just 10 seconds. Okay, that's one way to do it, right? Or graph it. Should I actually show you the graphing? Can't really see it on the PDF. That's sort of what it looks like. So I'm going to put down 700 meters on this side. This side's going to be 20 T's plus a half A. So that's 4.905 T squared. So what I would graph is this side is y1, this side, all of this side, as y2, and find out where they cross each other. So the graph's going to kind of look like this. This 700 right here. And then I'm going to have an equation, I think it goes, I don't know, this one's going to be, it's going to go this way. We got some negative times here too. It's going to go, wow. And then you're going to see that it's going to cross Got 10 seconds right there. Okay. Well, if you want to do that on your calculator, you can. That's fine. Okay, so vectors. We've been dealing with vectors this whole time, really. But I just have to remember that a vector is something that has a direction and a magnitude to it. Okay? So if I ask you to solve for a resultant, a resolving displacement, a resolving net force or something, you're going to need those two things. You're going to need your magnitude, which is like the length of the line, and the direction. And it's either stated in like polar coordinates or navigator method or standard position. The polar one we don't do that often. Okay. So let's resolve these into the components. So we've got 135 degrees here. Now, it doesn't specify a sign convention or anything. We're just going to get our x and y. So let's just assume for most questions that these two things are positive, because it makes it a little bit easier too. Oh. Alright, so if I were to draw out 135 right about here, that's 135 degrees. The magnitude of this line is 10, right? When they give you like a vector like this, that's always the hypotenuse. I want to find these two pieces, the x and the y, right? So I'm going to find the y position, because that looks like the opposite. And if you're given the standard position angle, sine, it will always be the opposite. So it'll be 10 meters per second, sine 135. Which is nice, because what's going to happen, it's going to give us a negative or positive, depending on which quadrant it lands in. So this will end up being positive, because we know it's going upwards. But this, remember, this only really works for standard position angles. If you keep the sign convention this way. Oh, I need 2 seconds. Okay, and the x component, which will end up being negative, but the calculator will spit out a negative number. We know it's supposed to be negative, and it will be negative. 10 cos, I should probably change that right away. 135, right? Not 35. What was I thinking? 2 mistakes with that. Oh, actually, I said 135. Cos 135. Okay, so 10 cos 135. Well, yeah, a negative number. These happen to be the same because the reference angle is 45 degrees. Cool. All right, so a dog, done a bunch of walking around. What is his overall displacement? Here, you're going to be adding all those x's and y's together. All right, so you got all these vectors, right? East, south, west, and so this one here, if I'm going east, that is all in the x direction, never, in the x direction, so this is like a positive x. This one's going north, so that's like a positive y. This one's a negative x because it's going west. This is a negative y, and this one's going back to a positive x. So remember, when you're adding these together, you can only add them if they're collinear to each other. So I can only add all the x's together, so I'm going to add all these x's together, and I've got to add all the y's together. So I got a positive 4 meters. I'm going to add a negative 6, and then I'm going to add another positive 4. So overall, it's 2, isn't it? 2, it's a positive 2 meters. And then my y's, I'm going to add those together. So we have 5 meters plus a negative 7 meters. You go to a negative 2 meters in the y direction. So now what we're going to do is we're going to take those and put them together, right? So I'm going to draw a new vector. So this is my resultant. I'm going to draw a new vector with this information. So I'm going to go in the x direction, 2 meters, and then I'm going to go in the y direction, 2 meters. Now, because it's negative, I'm going to go down, right? And my overall vector is that hypotenuse with this angle, right? Now, because I have northeast, southwest in this question, I'm going to be able to use northeast, southwest in the question. I can't just, but though I just can't say, oh, it's going southeast. I got to add in an angle onto it, right? So let's do the Pythagorean theorem first. So to find out the hypotenuse, my resultant, I gotta do the Pythagorean theorem. I gotta go 2 squared plus 2 squared, take that square root. 4 squared, 4 plus 4, 4 plus 4. So I get this 2.83 meters. But I need this angle, right? So to find that angle, I'm gonna go tan inverse. Got my opposite, 2. I got my adjacent, 2. So that's 45 degrees. All right. So I'm going to put my 45 degrees in here. But then I got to say what direction. So based on the way I drew it, I'm south of that east line, right? So I'm going east first. I'm going to go east first and then go south, right? So I'm going east first, then south. I'm not worried about that. We'll just cross that question off. Crosswinds, don't do crosswinds. Ignore crosswinds. Okay, projectile motion. Okay, so when you throw an object off something, or throw an object up in the air at an angle, you're going to have two pieces, right? You're going to have an x direction and a y direction, a horizontal and a vertical direction. What's interesting about that is that they act kind of independent of each other. Though they are sharing time, they do act independent of each other. So in the vertical direction, because there's acceleration, because gravity is vertical, I'm going to accelerate in the vertical direction. I got to deal with the acceleration. But horizontally, if I ignore friction, most of the time we do, if I ignore friction, there is no acceleration because there's no force in that direction. So I'm not going to change in the horizontal direction. So whatever horizontal velocity I have to start off with, I just keep it as I go. Okay. So here we have an object. It's thrown off a cliff horizontally. So I'm going to create my T-chart here. I'm going to run out of space to create a T-chart here. I might have to give myself a little bit extra space. I know you can't do this. I should have done that up here. Gave myself an extra space for all these questions, but whatever. How much more space maybe? I can go one more page. Nope. That's for you. Okay. So there's object here thrown horizontally off a cliff. Now the key word is horizontal. So that means in my T-chart here, because it's thrown horizontally, let's make the T-chart a little bit larger. In my vertical direction, where my acceleration is 9.81, my VI is 0. So my acceleration is down. Let's just say down is positive in this question. Makes my math a little bit easier. Don't have to worry about double negatives or anything. So A is negative, or it's downward, so it's positive. VI, nice, 0 because it's thrown horizontally. And, oh, it gives this time, which is nice. All right, 4.20 seconds. Okay, now what's nice about this is because we have the time in the horizontal direction, that's the same time. Wouldn't make sense that it would fall for a longer time than it traveled sideways. Why would it do that? It wouldn't make any sense. Because this is a horizontal velocity. That velocity is neither an initial, it is kind of an initial velocity, but it's the same as my final. There's no change in velocity here. So my initial and my final are both the same. So this is just like my V average velocity. And in the horizontal direction, my acceleration is 0, right? So what's nice about that? In the horizontal direction, I'm allowed to use V is equal to D over T. And look at this, this is how far from the base of the cliff does it land. So I'm looking for that displacement there. It's really just V times T. 20 times 4.2, so 84 meters. 84.0, because I need that extra 60 bit. Cool. What else do we have here? Let's see. Is that right so far? I can double check. Yep, it's 84. All right, so next one. Building thrown horizontally again. What's the velocity just before it hits the ground? Okay, so this is it's a more difficult question because velocity, remember, it has to have direction to it. If I throw something up horizontally, it's going to hit the ground at an angle. I'm going to have to find out what that angle is. But it's thrown horizontally. It lands a certain distance. What's its velocity? So let's see what we have. Okay, so what's nice? Thrown horizontally. So my vertical direction, where my A is 9.81 again. You notice I didn't use that last time, but I might have to use it this time. 0. We need to find, if I'm going to find the velocity of this object, this is the ball just before it hits the ground. It's going to hit the ground at an angle. I have to know two things. I've got to know how fast is it traveling horizontally and what is its final vertical velocity, so I can find not the final velocity vertical, but the actual velocity at an angle. So I'm going to need to find out what my VF is. What does that end up being? But to do that, I need time. I need something else. Like the vertical height. Oh, I do have a vertical height. I think I would need the time. Okay, but I don't. Okay, so I have a vertical height here. So the D is equal to, it's going down 85 meters. So I can just put in 85 there. And then just give myself a little bit more space. Yes, I can. I ran out of space here. Okay, push the other question off and get a page. Okay. And then find out what formula. So what did we have to use? Oh, we're going to use that VF squared formula, it looks like. So VF squared, because there's no time here. So VF squared is equal to VI squared plus 2AD. Just take the square root of all of that. Plug all the numbers in. Should get VF here. So let's see what we got here. 2 times 9.1 times the 85. Take the square root. So 40.8. Okay. Keep the decimals in your calculator if you can. 40.8374. Well, if you can. Apparently I can't, so I'm just going to go over here, put all the decimals again. So 3748. Okay. Now in the horizontal direction, we have the distance it traveled, 67.1. Oh man, this is a tough question. Oh. We have the distance it traveled, but to find that vertical or the horizontal speed, I'm going to need to know the time it took to do that, right? Because I had to go d divided by t. I don't think I have the t in this question. Nope. So I'm going to go back over to the vertical direction and find that time too, right? Because we're going to need it. Oh man, my thing is starting to slow down here because of how much writing I've done on this. Okay. So here I've got to find time now. So I don't trust anything else except for the top few things here. So I'm going to find time using this formula, VIT plus 1/2 AT squared, because VI is equal to 0. That's also equal to 0, which is nice. So technically the formula is this one. I'm going to times by 2 to get rid of the half. Divide by A to get rid of this A here. And then I just remember to take the square root to get t by itself here. Okay. So 2 times the 85 divided by the 9.81. Take the square root. So the ball or whatever object is in the air for 4.162 blah 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 seconds. So now what I'm going to do with that time, I'm going to take that time and go up here with it. Find out how fast this is moving horizontally. What about my time? So horizontally it's traveling 16.28694 meters per second. Okay, So now we have the two pieces I need for my triangle over here. Right? So my triangle, I'm going to redraw a little bit higher, has these two pieces. So it has a horizontal velocity of 16.28694 meters per second, and then it has a vertical velocity downwards, because I said down was positive, so everything was positive here, so that makes sense that this be a positive number because it's going down. 837 meters per second, and we're going to find out these two things, this angle of depression. I'm not going to find like the standard positioning, I'm just going to find that angle of depression. So, alright, so we got our two pieces. We're going to just use a Pythagorean theorem and find out what those would, what the hypotenuse would be. I'm just typing this number on the calculator here. So it looks like I got an angle using the tan inverse, right? Let's keep it red here. Tan inverse of my y over my x. I'm not going to write those numbers out again. I got 44 degrees. Let's just go with that, right? And using Pythagorean theorem, I'm going to find that resultant, which is the square root of like x squared plus y squared, to be the square root of that 16 point. This would be nice if I had a calculator that saved the numbers. I just go back and highlight them. Make sure I don't make a mistake typing them out, but that's fine. I might make a mistake. Just a second. Well, that's weird. 40, 4. Oh, never mind. The angle is not 40 something, is it? Bigger than that. Whoops. I did the Pythagorean theorem twice. So this is 44.0 meters per second. And the angle at which it's ground, because it is a velocity, I've got to find the angle. Look at my answer sheet, it doesn't have that angle. I haven't created an answer sheet. But we got to do this tan inverse here. Ah, there's 68 degrees. The angle of depression is 68. I'm just going to say 68 degrees. I'm just going to get my hands up in the air about that. It reaches the maximum height. What's the velocity it was thrown? So this is another one of those velocity questions. We have to find that hypotenuse, but which is nice about this one, they give us the angle. So I'm going to find one side of this triangle. So it's going to be thrown up at an angle of 30 degrees. 30 degrees. If I find one side of this triangle, I could find any other side, because I have the angle, which is nice. So if I can find the horizontal or the vertical piece of this triangle, I can use sine or cosine to solve for the hypotenuse. So what do we have? Well, let's see. We got, in the vertical direction, we have the acceleration, negative 9.81 meters per second squared. I'm saying negative because it was thrown upwards, so there is a vertical velocity that's positive, it's upwards. So that's what we're trying to find anyway. It tells us that we reach a maximum height. So height is vertical, which is upwards, nice positive number. We just have to, what else do we need here? Oh, because it's the maximum height. Our VF is 0, right? Because we're at max height. So actually I don't need anything, because I can find VI, and once I find VI, in my horizontal direction, I don't need this side, right? Not needed, right? Okay, so over here I'm trying to find VI. So it looks like I'm going to be using this formula. Not time. So this formula doesn't have time. We're trying to find a VI. So I'm going to take the 280 and minus it over to the other side. Take the square root of both sides. If I do that, where's my d go up to? Disappeared. Oh, VF is 0, so that's awesome. So I got negative 2 times negative 9.81. So 2 negatives make a positive, which is great. Times my d, and then the square root. So my VI is 10.62144 meters per second. But that's not the initial velocity, right? That's just the vertical component of that velocity. So this number here we just found is right here. But we're looking for that velocity. We're looking for that hypotenuse. So I'm going to be using, because that's the opposite side. That's across the triangle, so that's the opposite side. So I'm going to use sine. We have 30 degrees. We have the opposite. We're trying to find the hypotenuse. I'm just going to call it the resultant here. That's what we're looking for. Okay. So we had to rearrange this equation. So we're going to times the r up to the other side. And then we're going to divide the sine 30 down. A lot of writing here. Cool. Divide by sine 30, which is a half, if you remember your trig. So I get 21. Oh, I'm going to add space here. Ooh. 21 point. Oh, I got 360 degrees. 21.2 meters per second. Yay! Okay. Okay, I'm almost done. Okay. Once I finish kinemax, I'm going to stop this video. I'm going to head home and have some dinner, and then we'll figure out what to do for the rest of this. Okay, the same ball is kicked at a velocity of 25 meters per second. It travels for a range, is in the air. What angle was it thrown at? Okay, so it doesn't matter if it's the same ball at all. It's just a ball is kicked at some angle, which I don't know. So again, oh, it's not. Not 0 degrees. What if it, for some reason I'm putting zeros instead of question marks in some things here. Been doing it all day. So here I don't know what this angle is, right? So to find the angle, I'm going to need two sides of this triangle. I'm going to know the VI and the V or the hypotenuse, which I know. I know the hypotenuse. This is great. So actually I only need one more side for this triangle, right? Oh, don't erase that. So my program is getting a bit slow here. Let's see, it's glitching out here. Okay, so VI and V. So if I find one more piece of this triangle, so we got a range, we got time. Oh, that's enough. So the problem is that when I try to solve for VI, I don't think I have enough information for the vertical section, right? So in the vertical section, A, which is downwards, it could be negative 9.81. We want to try to solve for VI if we can, because if I solve for VI, I had the hypotenuse. Use sine to find the angle. Oh, what else do we have here? I don't have anything else. Doesn't talk about max height. I guess it could come back down to the ground. Yeah, this talks about range. It doesn't say that it comes back. Nothing there. Okay, so in the horizontal direction, though, what do we have here? We have the range, so that's the horizontal distance it travels. It has the time, 2.15 seconds. Well, that's enough because remember in the horizontal direction, A is equal to 0, that means V is equal to D over T, and we have both those things. Right? So let's just find that V really quickly. So 11.6279 meters per second. Okay, so now we know that. That's this. That's this number right here. 11.6279 meters per second. So now we know the adjacent side. We have the hypotenuse. I'm going to use cosine. Okay, so I don't know the theta. I don't know theta there, but I do know the two sides. I'll fill as much as I can on my equation. But then I got to figure out a way to move the cos over to the other side, right? So to solve for theta, we've got to take the cos inverse of both sides. I'm going to write that down here. Cos inverse, cos inverse. The cos inverse is going to cross that off, right? So I get theta by itself, so I got to do cos inverse of 11.6279 over 25. Yes, there's no units in work because they crossed off, but so cos inverse of my answer for my previous question, I'm going to use all the decimals I can, divide by 25, and I get an angle of 62.3 degrees. Just make up the sig digs when it comes to angles, really. All right, so that was a nice little hour and 10 minutes to go through the first few pages. I'm going to post this, obviously this video, you'll probably, if you're watching it, post this, and then I'll post the second half of this tomorrow. I'll come back, finish it off. That's the first half of the questions. Then maybe I'll also post the answer key for the other practice final I probably just posted, and I'll see you then. Bye.